Hello and welcome to this Unisensor microsensor lecture. My name is Lars Hauer Larsen and I am CSO here at Unisense and responsible for production and development of Unisense microsensors. In this lecture, I will explain how potentiometric microelectrodes generally work. Unisense currently sells two types of potentiometric electrodes: the pH glass microelectrode and the redox potential microelectrode. The measuring principles for these two electrode types share a lot of similarities, and therefore I will give a general introduction to potentiometric microelectrode measurements in this lecture. Web lectures specifically on the pH and redox microelectrodes are also found on our website, so please continue to these for more information about these specific electrode types after having followed this lecture. This lecture will cover the following topics: the measuring principles, need for high impedance voltmeter, reference electrode and calibration, combination electrodes, interference from electrical noise, and electrical fields in setups. The detecting principle is measuring the electrode self-potential as a function of a chemical change in the sample. This can be measured if the electrode is connected to a reference electrode, which potential is not affected by the chemical change in the sample, thus the term reference electrode. The electrode and the reference electrode must be placed in the same sample solution, which acts as a salt bridge, making the electrode couples a complete electrochemical cell. Electrons will tend to flow from the electrode having a more negative self potential than the other, creating a small current, a battery. If the potential of the electrode relative to the reference electrode changes from negative to positive, the electron flow change direction. The current running is, however, not a very good indicator of the potential change of the electrode, because the current is not stable and will depend on the electrode capacity, which is not very big for a microelectrode. It is much better to measure the potential difference. To measure the potential difference, a millivoltmeter must be inserted between the electrode and the reference electrode. A millivoltmeter measures the potential by using principles of Ohm's law, U equals R times I, where R is the impedance of the meter, which is constant. Thus, the measured current I is proportional to the potential. A millivoltmeter used for microelectrodes must have a large impedance, so only a very minute current is running between the electrodes, otherwise the potential measured is not stable. The importance of the meter impedance is illustrated by this water pipe analog. The water plant sends out pressurized water, but at the end of an open pipe the pressure is low due to the pressure drop from the plant to the open pipe end. If the valve is closed at the end of the pipe, the pressure at the end of the pipe increases to approximately the same pressure as at the water plant. If the valve opens somewhat, the pumping capacity of the plant influences how big the pressure drop will be. Therefore, the capacity of the potentiometric electrode to deliver or accept electrons to maintain the potential determines the necessary impedance of the millivoltmeter for measuring the potential correctly. The smaller the electrode is, the more impedance the millivoltmeter must have to measure the potential difference between the electrodes. Due to the tiny surface of the Unisense potentiometric microelectrodes, we recommend that the meter must have an impedance of at least 10 to the 13th ohm, and therefore we only guarantee the specs of the electrodes if used with a Unisense meter. The measured voltage of the millivoltmeter is the sum of the potential of the microelectrode, the external reference electrode, and the liquid junction. The reference electrode and the liquid junction are constructed so the potentials do not change with sample chemical changes, and therefore only the potential at the electrode tip must change to change the sample. Imagine now that a potentiometric microelectrode and a silver chloride reference electrode are placed in a sample. The millivolt meter's display shows 150 millivolt. Then the reference electrode is replaced with a calomel reference electrode, and the display shows now only 80 millivolt. Why? Recall that the measured potential is the sum of the potentials of the microelectrode, the external reference electrode, and the liquid junction. Therefore, the potential measured is always relative to and dependent on the reference used. Therefore, electrodes must be calibrated and used for sample measurements with the same reference electrode. For measurements in small samples, for example samples in test tubes where space is limited, it might be inconvenient using an external reference. For such measurements, a combination electrode is a better choice. We make such electrodes only in 500 micrometer versions of our electrodes, and the distance between the electrode tip and the reference opening is 2 to 4 millimeter. The reference opening must be inserted into the sample. For very small sample measurements, we can shorten the distance between the reference opening and the redox or pH electrode tip. As the reference capillary make the tip bulkier, there's no reason to make versions with smaller electrode tip diameters. The reference consists of a capillary filled with a jellified potassium chloride electrolyte, with a connection to a potassium chloride filled reservoir with a silver chloride reference electrode. Potassium chloride is chosen because the dissociated ions diffuse almost with the same speed and therefore no charge separation takes place at the liquid junction. However, when measuring in, for example, seawater, different migration speed for sodium and chloride could change the junction potential somewhat, which potentially change the measured cell potential. Recall that to get correct measurements, only the potential of the electrode must change with the sample chemical change. If the tip junction potential changes when moving the combination electrode from the calibration buffer to the sample, measurements could be slightly affected. If you have room for an external reference, it is therefore recommended to use this. Larger reference electrodes with porous junctions like Unisen's reference RM are designed so that tip liquid junction potentials do not build up. This junction does, however, leak ions out to the sample from the reference electrolyte reservoir. So if you have small samples which are sensitive to salinity increase, the Unisen's combination electrode is a better choice. The reference opening on a Unisen's combination electrode is only 10 microns in diameter, and thus the contamination is minimal. The measurements with potentiometric microelectrodes can easily be affected by electrostatic charges and electrical noise. The signal chain, the electrode body, cables and connectors are well shielded, but because the cable connects between ultra-high resistances, electrostatic charges which accumulate on cables and connectors cannot readily be drained away, so environmental factors affect the detection limit. Even people walking by might introduce such noise on the signal. Therefore, take actions to ensure that such interferences is minimized as much as possible. Measurements done in situ would typically be less noisy than laboratory measurements. If signals from an electrode fails to become stable and drifts a lot, it could be due to electrical fields affecting the measurements. If the electrode/reference pair are placed where electrical fields are present, this will affect the millivolt signal and thus the calibration curve. Imagine that on both sides of the microelectrode and reference electrode are placed other electrodes and a voltage source applies potential between these two. This will result in an electrical field within the measuring solution. This is illustrated here where a microelectrode and a reference electrode are placed in an electrical field between an anode and a cathode. The potential drop between the electrodes will be added or subtracted from the millivolt signal measured by the millivolt meter. Electrical fields can arise unintentionally in setups where static electricity builds up or if other lab instruments are not connected to common ground. Especially, it is our experience that potentiometric microelectrode measurements in ship laboratories suffer from these phenomena due to lack of common ground of electrical installations. Also, labs that suffer from static electricity discharges could see electrical fields in setups. Obviously, the closer the reference is moved to the redox or pH electrode, the smaller the potential drop will be, and this could minimize the problem. Thank you for watching this Unisense microsensor lecture. I hope you enjoyed it. If you have any questions, you are more than welcome to contact us at sales@unisense.com.